So good evening, everybody, and welcome. I'm Fergal Finn, and I'm representing NSAI. So I work in the standards development section of NSAI. It's part of the public good that we offer and is not a commercial venture. So I'm not here to sell you certification. We have a couple of other divisions in NSAI also carrying out public good. So I'm going to focus on the standards development aspect of things just real quick. What are standards? So standards are documents that are voluntary in their application. They're established by interested parties and they reflect a consensus by those that are drafting the standards, and they're meant for a common and repeated use. A standard is quite a simple document in that it sets out a set of requirements in the form of a shall statement in the document. It can prescribe methods, also using the shall statement and prescribing the method that is required. It gives recommendations in the form of should statements and offers guidance in the form of notes in the document. Just looking briefly at European standards organizations, what we have is at the CENELEC side, they produce all of the European standards for electricity and electrotechnical, okay? And CEN then produces all of the services and product standards for everything else, shall we say. And we also then have the ETSI, who provide the standards for the electronic communication. So if we were to look at a mobile phone, the CENELEC guys would do all of the circuitry standards. The CEN guys would do all of the material standards for the structure of the phone. And the ETSI guys would do all of the standards that make my phone talk to your phone, okay? That's then based on what we have internationally, where we have the IEC doing the electrical and electrotechnical standard, the ITU providing the communication standards, and then ISO providing all of the other services, management standards, and product standards globally. We also then have industry standards. So an industry standard is a standard that's produced by industry for industry. A few of the examples that I've given here are the API standards written by the American Petroleum Institute, and they're used in major parts of the world. However, the API standards have now started to be adopted as ISO standards, and those ISO standards are being used globally. The ASTM standards, as engineers, you'll most likely come across ASTM standards. They have standards for absolutely everything, especially for materials, and they're quite a fantastic standards organization. IGEM, this is a group of engineers in the UK who take European ISO and British standards, and they produce codes of practice which are used or accepted as industry standards in the UK. And another example is the VD, a German association of engineers producing industry standards. So where does NSAI sit in the whole lot of this? So we're a national standards body, and we are members of CEN and CENELEC. We are also then members of ISO and IEC, and our standards activities are traverse across European and international regions. In Europe, there's 28 EU countries or 33 members. And in ISO, there are 162 members, of which Ireland is a member. We carry one vote in ISO, the same as every other country. So the Irish vote is the equivalent to that of the US, the UK, Kazakhstan, etc. So we have one vote, one country. In the ICT standards, a lot of the members of these organizations are actually representing themselves, their own companies. In CENELEC, ISO, and IEC, the members are the national standards bodies from each of the member countries. So the process for writing a standard, it's about 3 years, give or take. It starts out with a demand, and a decision is made as to whether or not that work should go ahead. Once the work goes ahead, we spend about 2 years drafting the standard with a group of experts made up of industry, academia, consumers, and regulators. This gives us a multi-stakeholder input and ensures that the standard is as balanced and as fair as possible. When that standard is written, it goes through a consultation process. In ISO, everyone in the world gets a chance to comment on the standard. And in Ireland, we publish our standards on a platform called Your Standards, Your Say. So everybody has the opportunity to comment on any draft standards. After the consultation process and the document has been ratified, we publish that document, and then it is put out there for utilization. And 5 years later, we do a systematic review on it. Now, looking at the additive manufacturing standards, pretty much for the first time ever, when this new emerging technology came about, and the standards organizations looked at how they were going to standardize this new technology, they decided that they would do one set of additive manufacturing standards. One world, one standard is their motto. And we have established a partnership. So ISO and ASTM have a partnership together whereby they together produce the ISO ASTM standards for additive manufacturing. The Europeans have agreed to adopt all of those standards as they are published. So where these standards are developed is in the ISO Technical Committee 261, Additive Manufacturing, which the Secretariat is held by Germany. There are 25 participating countries. That means that from 25 countries, the experts that are writing these standards are coming in from there. There's also a number of observing countries that don't participate. To date, they have published 19 standards and have approximately 37 standards under development. They're split into working groups, one in terminology, 2 methods, process, and materials, 3 test methods, 4 data and design. So they were the 4 originals. Since in the last few years, then they've set up new working groups looking at the environmental, health and safety aspects. And they have a joint working group on aerospace. So the Technical Committee on Aerospace and the Technical Committee on Additive Manufacturing are working together to produce additive manufacturing specific standards for aerospace. And similarly in the Plastics Technical Committee and the Additive Manufacturing Committee have joined to produce those standards. So just to give a quick rundown of the structure, at the very top level at our technical committee represented by the member states, we hand down the work to any one of the working groups. Within those working groups, there are a number of joint groups, and this joint group is made up of ASTM and ISO members. These small groups tend to be made up of about 8 to 10 experts, and they will be producing 1 or 2 standards each at any one time. So it's quite controlled, but somewhat chaotic at times, and a lot of work going through. So just a quick look then at the process, okay? So the standards in additive manufacturing. We started off with terminology. It was one of the, it seems to be one of the most important standards that we write now when it comes to new and emerging technologies. In quantum computing, we have agreed that the first standard we'll write for quantum computing is going to be terminology, because at the minute, everybody's calling different stuff, different names, and it's getting somewhat confusing. The terminology standard allows us to have defined terms and definitions for the different aspects of that process. So looking at the data and design, we have requirements and guidelines, functionally graded additive manufacturing design, laser-based powder bed fusion of metals, laser bed fusion powder fusion of polymers, a number of standards then dealing with the data, and there are still a number of works in process dealing with just the data aspects of additive manufacturing. On the materials side, quite a lot of work has been done on both polymers and metals and the feedstocks for that. I'm only listing the ones that have been published to date. On the personnel side, the aerospace boys were rather quick to get up and do some qualification standards for the operators, and there's still a number of other standards in development, all centered around the qualification principles of the personnel involved. In the process then, there's a number of standards already published and many more in development. And again, we have one particular standard on the acceptance testing for the aerospace applications. On the testing and inspection, a number of standards now. The whole QA, QC, the non-destructive testing, the analysis of 3D printed parts or additive manufactured parts has been quite challenging and brought up a lot of discussion. So these have been exciting standards to get over the line in the area of testing and QA, QC for additive manufacturing. And just to give you a very quick glimpse of what's being developed at the moment, the intentionally seeded flaws, again, testing, round robin studies in additive manufacturing, the NDT of manufacturing, personal training, the requirements for purchase parts. So pretty much they are looking at the every aspect of additive manufacturing, start to finish. The ISO standards are being adopted as European standards, and those European standards are being adopted as Irish standards. So what happens is our ISO ASTM standard is published, it's adopted as a European standard, and then adopted as an Irish standard. What's the difference between a British standard and an Irish standard? Nothing really, only the price and the cover sheet. The British standards have a picture of fireman on front of theirs, quite nice. Ours, black and white. On our National Mirror Committee, we have a lot of members representing quite a number of organizations across industry and academia. And they're helping us to monitor the development of the standards. What we do is we bring these people to the table, give them access to the standards writing process, and give them access as well to the international standards organizations where they can get involved in the standards development. If anybody wants to get involved in the writing of a standard, and it is quite exciting. We have the link on our website to register your interest, and you can ask us then if you'd like to get involved in the additive manufacturing committee. So just to wrap it up, standards, they're all a part of our manufacturing industry. You can see the standards as they develop in additive manufacturing, and you can be part of the standard as it develops. NSAI is here to help you. Just call Fergal. Okay, thank you everyone. I'll pass it over now, John.
Thanks very much, Fergal. That's very interesting just to see how it all comes together. As I said, we'll have questions at the end, so please do submit anything that you have in the Q&A. And now we'll go on to Dermot Brabazon. Dermot is a full professor in the School of Mechanical and Manufacturing Engineering at DCU. He is the director of the Advanced Processing Technology Research Center, the Advanced Metallic Systems Research Center, and Deputy Director of IFORM, National Advanced Manufacturing Research Center. He leads projects on both the fundamental development and applied and the applications with company partners in the areas of material science and engineering. And he's going to present tonight on the process control in additive manufacturing. I'll hand over to you now, Dermot. I think you might be muted, Dermot.
Thanks very much, John, and good evening, everybody. I'm covering the process control side of the presentation this evening within additive manufacturing, and specifically focusing towards metal additive manufacturing. So here are some examples of the metal additive manufactured components. The top left image shows the GE LEAP engine, which was more than 25 components originally made by 25 separate processes, and now is metal additive manufactured in one process. So this saves a lot of cost from processing, but also is a technically better solution than manufacturing all of these components separately and then trying to get the joins to be leak-proof and the quality assurance around getting leak-proof joins on those 25 separate components. So it's an example of additive manufacturing enabling the joining of components in one process rather than having separate production and assembly steps in the production line. Just below that, it shows a dental amalgam, and implants and biomedical applications would be another strong area for usage of metal additive manufacturing. In the middle, we see two pictures of brackets that are used for aerospace. The bracket at the back in both cases is the original bracket, and the bracket at the front is a topology optimized bracket, whereby 3D printing complicated personalized designs for the solution can be printed. In this case, reducing the overall weight for that component, but still meeting the functional requirements for joining two sections of the plane together. On the right-hand side, it's engine turbine blades. And in this case, while the components on the left are manufactured completely by laser powder bed fusion, the components on the right tend to be repaired by direct energy deposition, which Bryan is going to talk about more in the next presentation. I'm going to concentrate on this presentation a little bit more on the laser powder bed fusion mechanism. This is an example of a typical laser powder bed fusion laboratory. On the left-hand side here, we see the computer, the CAD file is generated, it's converted into an STL file, and it's converted then into a step file and a sliced file eventually for the metal additive manufacturing machine. And a lot of those final files for the actual operation of the machine can be bespoke for the machine itself. So there's a little bit of processing of the CAD file to get it to be brought into the build file for the final machine. The process parameters on the machine, the metal additive manufacturing machine we see in the middle, can then be altered as well, like power and spot size and setup. We see a quantity printer and some pyrometry measurements in line with the laser as the laser comes down and solidifies the metal in the system itself, and then some other powder handling components. Looking at this in a little bit more detail, the laser is coming in here, going through a galvanometer, and then tracing out a path in the powder. And we have a little video here to show that. The laser tracing out the two-dimensional slice of the CAD file, solidifying that powder into that two-dimensional geometry. It's being bound onto the previous two-dimensional geometry, and now the powder recoater is pulling powder across and recoating powder, a fresh layer of powder that's set in terms of the size of that layer of powder. It could be 20 microns, 30 microns, 40 microns of powder being recoated on top of the previously solidified layer. And then the next layer is subsequently being melted and bonded, micro-welded into the previous layer. And that process keeps repeating until the final component is produced. All of this in an inert atmosphere. So the process parameter inputs here: laser power, scan speed, scan strategy, layer thickness, laser beam spot size, taking the power and the spot size to give the overall energy density, and then the energy density per time when we think of that in relation to the scan speed and pulse repetition frequency if the laser is being pulsed. and then the powder properties as well. In terms of in situ measurements, we can measure the infrared temperature data for the spot where the laser spot is, camera imaging of the process, ultrasound imaging, radio emission spectroscopy, optical emission spectroscopy, in situ measurements of the process to understand the quality of the processing. And then we measure on the output side the porosity, the surface roughness, the macroscopic dimensions, the mechanical properties, the internal phase structure and chemical structure to give those mechanical properties as well. Just in the images here, we see on the plate 17 samples and the IR data from one of the layers of those 17 samples. That is indicating the temperature for that particular layer during production. From that data, we can infer a pore that occurs, and this is a metallography sample, a cut through and polished and etched section, where at high magnification we can see the pore, or in micro CT. So we have a number of post-processing techniques to measure the actual porosity, and then some in situ processing techniques where we apply these to understand the quality or the porosity that's occurring during the process. It is a very complicated process. There's many, many process parameters, but really only the main few we know are most important we can concentrate on in terms of process optimization. So we take the CAD file, we take the powder properties, we process it through the machine, we take the in situ monitoring data, and we take the ex situ diagnostic data, and we feed all that data back to give a better set of processing parameters in an iterative manner to come up with the optimized processing parameters. There's an example here showing for a rocket fuel valve and testing different topology optimizations for that component. In terms of the in situ and ex situ diagnostics for process quality control, this is needed because a lot of the times we're using different materials or different geometries or a different machine. And in all cases, the process parameters change to give the optimal output with no defects that has the correct quality for the process. In terms of commercial machines to date, all of these are still open control processes. So we can understand from in situ monitoring that the process is either in control or out of control. To give one example of where that can be implemented, this is an example of the laser beam going down to melt that powder, and the light of that going back in the infrared spectrum or in a different wavelength to a photodiode or infrared pyrometer to measure the actual temperature at in each location within the build. So we have a vast amount of data, literally into the terabytes of data, and the data handling then becomes an issue. How can you actually process and handle all of this data? And really the best way to do that is using machine learning techniques rather than individually to look at the data streams. So this is an example of 4 layers of data. For this example here on the right-hand side, it's an array of 9 by 9 samples. So that's 81 samples, and that's according to a conventional design of experiments where there's 3 parameters at 4 levels. So that's 81 sets of parameters that we're trialing. And we can see the results of the temperature on each of 4 of those layers. So if we take these 2 samples up here, these 2 samples are quite hot, i.e. more red in this case in terms of the color map, relative to some of the more green or yellowish samples. And if we take that from layer at 1 millimeter to layer at 2 millimeter, layer at 3 millimeter, we can see that the process parameters are having an overriding effect on the overall temperature and temperature gradient, which relates back to the microstructure and the porosity that generates during the process. That allows us to understand, do we need to actually stop the build? We know the part is not going to be correct, so we can stop before we actually go through hours of printing and end up with a part that can't be used. So we can understand from the in-process monitoring data that the process is in control or out of control. So this helps to reduce costs, overall costs in the process. It helps to achieve production gains in the process, and ultimately it helps to achieve best product performance as well, that we know it's in the requirements of the end application, and we know the sensitivity of that to the overall process parameters as well. If we vary the process parameters slightly, can we be sure that we're still in control from the in-process monitoring data and even from the process parameters that we set? As an example of that, just in terms of how or why a defect may occur, this is an example of some of the areas where porosity may occur. It may occur due to lack of fusion, intergranular liquid region being cut off during solidification, gas evolution during solidification, solidified undulations during the vapor phase and the plasma that's being generated, or it could be due to keyhole formation where there's overheat presented into the sample. So this is lack of fusion. And here we see the pores being trapped by the solidifying liquid, where there's the belt pool is too large, and this X-ray during the process shows us that that pore is then trapped into the part. Generally, keyhole formation and lack of fusion are just designed out very quickly from design of experiments, and then we refine in order to get the overall part to be as we want it to be. So we do these screening tests, we do then design of experiments, then we do sensitivity analysis on the selected parameters, and then we finally do either design of experiments in depth, or more often now design of experiments also with machine learning to get to the optimized solution even more quickly as an advanced statistical approach. One of those machine learning techniques that we use is Bayesian optimization. Using Bayes' theorem, we can then run a design of experiments, and rather than us deciding what next set of parameters to trial, we can run it through a Bayes' theorem or Bayesian optimization, and from that understand what are the most optimal next design of experiments can we run in order to get to the correct process parameters more quickly. So we can iterate that through using Bayesian optimization to get to the optimized solution more quickly than in conventional design of experiments. So just as an example of how we might use this machine learning algorithm, we would have the input parameters that we want to vary, we would have the output parameters that we want to measure, and we would run it, for example, in this case, according to a box Becken design, then pass those results through a Bayesian optimization, and that allows us to select the process parameters for the next box Becken design of experiments, and we iterate through that process to get to the solution more quickly. Just to give an example of where this is in industry right now, there's a company called Intelligence working with University of Sheffield and Boeing, and they're using machine learning to optimize the metal additive manufacturing. And in this case, they suggest in this recent article from January this year that they can reduce the number of experimental cycles by around 80%. Just to give one more example of that, the company Materialize in Belgium have also introduced a very similar software that is using the advanced statistical approaches also in the software that they have termed as process or called Process Tuner. In this software, then they achieve similar reductions in the overall number of experiments that are required to achieve the final solution more quickly. I'm just going to give a brief overview of how iForm is helping to achieve these solutions for advanced manufacturing, including additive manufacturing, by using the digitization of additive manufacturing, using fundamental process modeling, and then using advanced analytical machine learning techniques, combining all of these three areas to come to the solution more optimally for advanced manufacturing processes. And then within iForm, of course, we have a lot of our activities working directly on company projects for specific applications and end goals. I just briefly mentioned we have an advanced metallic systems center for doctoral training where we hire 25 to 30 PhD students, and these projects all have to be linked into company problems to solve company problems. So it's a strong collaboration. Also in terms of the training, the students get training from Manchester, Sheffield, UCD and DCU in terms of their overall training program, and have to work on a metallic system problem for their PhD related to solving a company problem. We also provide training courses to industry. As an example, we provide innovative materials for Industry 4 under the Human Capital Initiative. So if there's any industry partner looking for training, we can offer bespoke training initiatives through these types of schemes across iForm and the institutions. So thank you very much for listening, and looking forward to questions later. Thank you.
Thanks very much, Dermot. That was very interesting. I've seen there's a couple of questions already, so as Dermot said, please do get your questions in for all of the presenters. The third presenter today we're going to have is Bryan McAuliffe. He's a product engineering leader in Lufthansa Technik Turbine Shannon, and will be presenting this evening on the journey LTTS have undertaken to develop a novel approach to the repair of aerospace turbine components using additive manufacturing. Laser blown powder direct energy deposition was identified as the process to use to allow repair and the extension of life of these components. Okay, I'll now hand over to Bryan to run through his presentation.
Thank you, John. Thank you for the introduction and welcome everyone. So hopefully I can give you an insight into our use case of additive manufacturing in the aerospace sector. So just to give you initially a company introduction, then we give you a project overview. We'll explain what the component we're utilizing additive manufacturing to repair, which is the turbine seal segment. We'll explain the blown powder laser metal deposition process and why we specifically utilize this additive manufacturing technique in our repair. We'll explain some of the challenges that we encountered in our journey, also some of the validation steps that we undertook, and finally some of the conclusions to our project. So Lufthansa Technik is one of the sectors within the overall Lufthansa airline group. That includes passenger transportation, logistics, catering, and other activities. As mentioned in the video, we were founded in 1992, joint venture between GP and Sulzer, acquired in Lufthansa Technik in 1996, purpose-built facility. We have EASA, FAA, AAC, TCCA, and DGAC approvals. We're also ISO 14001, 9110, and OHSA 18001 certified. We're Engineers Ireland CPD accredited, and we have a current workforce of approximately 200 people. So to get into the technical side of the project, we utilize additive manufacturing for the repair of Rolls-Royce turbine seal segments using blown powder metal deposition, which is a specific additive manufacturing technique. The engines we specifically work on is Rolls-Royce turbofan engines. Rolls-Royce are one of the main aerospace engine suppliers globally. Their engines have up to 97,000 cubic pounds of thrust, a bypass ratio of as high as 10:1. So the seal segment, where that fits in the overall engine. As you can see here, this is the hot or high pressure section and intermediate pressure section of the turbine. The seal segment is a static component which sits in the outside area of this ring. The turbine blades, while they rotate, they abrade into the seal segment. That seal initially creates a barrier against gas flow leakage, thereby increasing the efficiency of the engine. So over time, that red surface you can see in red will wear away, increasing gas flow leakage and hence engine efficiency. So how we repair this component. Laser metal deposition is used to generate the abradable support structure that has been worn away. The repaired seal segment is required to perform equivalent to the OEM design. By doing this repair capability, it allows the maximization of life cycle cost and enables economic viability. Currently, a seal segment would be replaced with a new during any overall visit. So this allows the opportunity to replace with a repaired segment at a fraction of the cost. So just to explain some of the images here. On the left, we have a seal segment, which would be after undergoing a number of thousands life engine cycles. This is how we would receive it in LTTS. We would pre-machine the worn surfaces. We would then, in the top image in the center, we would use laser metal deposition to rebuild that structure, which you can see a final version of below that. Then we would fill this support structure with a sinter material and heat treat or cure this. So it would now form a new abradable structure similar to AM. So why did we use additive manufacturing for this specific repair? So additive manufacturing and laser blown powder specifically enables to repair components which are exposed to harsh high temperature environments, which are not suitable for conventional repair techniques. For example, like braze or honeycomb repairs. It also allows the feature addition of thin wall structures. So you have, as we say at the bottom point, a great degree of design flexibility and access by allowing this very accurate geometry to be deposited. It's also an adaptive process, which in this case is very important because we have varying part geometry and wear profiles that we see. Every part that comes into a shop is typically unique in its wear profile. So to explain the blown powder laser metal deposition process in a bit more detail, you have an additive layer methodology, similar to what Dermot was mentioning earlier, where we will deposit a layer. Initially, this layer will be embedded in the base material, so it will form a strong bond embedded within that. We will then build layer on top of that. Each layer has the ability to be a slightly different geometry, layer thickness, layer height, by varying our inputs. This feature addition also allows us to access restricted areas, as you can see there with some high wall structures and extended nozzles to get in, access these areas. Some of the material challenges we encountered, typically in aerospace, the materials we use which suit the engine environments are difficult to weld. This specific material, we use the base material is a single crystal superalloy. So the support structure superalloy material is designed to maintain its strength and oxidation resistance in harsh operating environment. There is also low dilution rates required so that the base material can retain its mechanical and thermophysical properties. Some of the process challenges that we then encountered is mainly around component and wear. Each segment, as I mentioned earlier, comes from a different engine with unique life cycles. Each individual segment has unique wear profiles that needs to be accounted for. No two parts will ever be identical, which makes standardization of the process more difficult. So we had to come up with a flexible repair process that is adaptive to each unique part. And our deposition process, program and parameters can revolve around this adaptation. In relation to the challenges on the deposition process itself, our requirement is for very thin wall support structure with very tight geometric tolerances. We have a very small laser and powder spot size, which would be at the lower end of the LMD process typically. Very highly restricted access. So we've undertaken a joint development project with ILT Fraunhofer in Germany, where we've developed a bespoke nozzle, which you can see in the image there, which is a very narrow body nozzle that allows us access difficult to reach areas. We also deposit at compound angles to the substrate, which allows us even greater access, as you can see in the image. But by doing that, it also provides some challenges in having melt pools at various radiuses and slopes. So we've done extensive DOEs, as Dermot mapped out earlier, with a very similar process where we've identified our inputs, our key inputs then from that, and also the effect of various slopes and radiuses to these inputs and identified a key process window from that. Some of the other process challenges is around the control, monitor, and stability. So we've over 60 controlled input variables associated with laser. So we have laser power, laser spot size, laser quality, we've powder feed rate, powder stability, we've nozzle wear, which is a very big key parameter for us. So our process is never at a fixed point. So our nozzles wear from the inside out due to the abrasion of the nickel superalloy powder. In doing that, we have to adapt our inputs with powder feed to meet a fixed output. So we have to constantly monitor and input control plans that closely control this. So I have an embedded video here of the deposition process, which you can see in a bit more detail than earlier. So this is a close-up view. It will run initially at normal speed, and it will jump on just to show you an actual additive build structure. So this will run layer by layer. So initially the first layer is currently embedding in the existing surface of the base material. As the tool pack comes back over, it will deposit another layer on top of that, and so on and so forth. Each layer has a unique geometry, unique thickness, a unique set of parameters, so that you can come up with an overall structure. There's also design flexibility there, then depending on the base material geometry, access requirements, you can adjust to suit. So as you can see there, we've jumped ahead. We've seen probably half of the additive structure built here. We build a different number of structures in different parts. So as you can see here, this is the first structure. There's also a similar structure above that that will be deposited next. But some components in the family that we repair have 1, 2, or 3 different structures all in one part. So hopefully I won't go to the end of this video because it's quite long, but it might give you a good insight into the start, middle, and end of that process and how those final structures actually look. So from a validation perspective, it's quite extensive, as you can imagine, in aerospace. In collaboration with our OEM partner, we've undertaken extensive validation through earlier mentioned DOE studies to identify, from a QA perspective, the key parameters. We created, as you can see, our virtual tour, bespoke process monitoring systems that give live feedback and also trained in SPC. We also then, for each product family, we will provide a set or a half set of engine test parts that will be engine tested in a test cell. So they'll undergo representative cycles that they would see in service. So you can see an image here of that deposition structure you would have seen in the previous video. This is after approximately 2,000 cycles of a typical 3,000 cycle test, which would represent a life cycle of an engine before it has to come in for maintenance, repair, or overhaul. So as you can see from this image, you can still make out individual layers in that structure. The vast majority of it is still intact, even after the harsh environment of mechanical stresses, oxidation, and corrosion. So we've seen equivalency to OEM parts in our engine testing to date on different products, which is very important in our sector. So just to conclude, the increased utilization of laser blown powder technology has provided us with opportunities for extended component life, and it also supports material sustainability. Adaptively repaired turbine components have demonstrated excellent performance during Rolls-Royce Trent engine tests and supported entry into service. Manufacturing capability was now entering the pre-production phase, and actually since this pack was developed, we've entered into early production phase, and we have plans for multiple different product families of seal segments to be validated and put into industrialization in the coming years. So that's my presentation. Hopefully that gave you an insight into our journey with additive manufacturing and the use case LTTS have. Thank you very much.
That was great, Brian. Thank you very much. We've got some questions in the Q&A. Again, if anyone has any more, please do send them in. I'll start off with one I have for Fergal. You mentioned consumers as part of the stakeholders in the development of standards, and I'm just wondering how you find those people. I think there might be an issue.
Sorry. They're actually the hardest representative group to find. And how often they're represented on committees is as associations or organization groups. So you're not going to get a guy coming in off the street to sit into one of our committee meetings and input. So it's done in quite a structured manner. But yeah, that is absolutely a challenge.
Thanks. Dermot, we had one came in from John Coleman. Actually, I had two from him, so I'll start off with the first one. Yes, many components manufactured by 3D printing are very complex in shape. How do you ensure that stresses are minimized in the component to guarantee long-term working life? Also, what drives the material selection when choosing the powders? I think muted there.
So a lot of finite element analysis is performed and can be performed. So predictive modeling of what would happen during the metal additive manufacturing process. So as an example of that, in ANSYS software, there is an additive manufacturing module, which includes Inconel, stainless steel, titanium, and it's been expanded all the time in terms of the alloys that are available through it. And through that, you can predict from the microstructure and resulting defects that may occur during the process if the process parameters. So you can apply the process parameters to a specific geometry and see what the resulting part would be like. Just in the answer to the second question from John on the material selection is often driven primarily by the end application. So in the aerospace industry, you see Inconel, nickel, titanium, cobalt, chrome, titanium, 6 aluminum, 4 vanadium. Some of those alloys overlap with the biomedical industry in Ireland. So it's titanium, nickel, titanium, cobalt, chrome, stainless steel. They're applied also in the biomedical industry. And then another industrial sector would be the tooling industry. So M2 tooling, raging steel, H13 for a high temperature tool steel. So it depends on the final application more so. And when interesting that Fergal presented some standards specific to the aerospace industry earlier. A lot of the standards that the aerospace industry and the biomedical industry would use are specific to their industries, and they still use those standards. They're not going to change in terms of the FDA regulation or the overall aerospace regulations on those industries. I see a question from David Tanner. Can ANSYS provide post-heat treatment in the microstructure? It's actually, we have a project with ANSYS at the moment, David, and we're working with them to develop post-heat treatment control of the microstructure. They're actively incorporating that into the latest versions of the software. So they typically come out with maybe two update versions of their software each year. And right now, the post-heat treatment of the additive manufactured component is being integrated into the latest versions of their software. That's obviously a time issue where the experimental validation of those models has to be implemented before the final model can be released. Yeah.
Okay, great, thanks. We had a question in from Niall Piggott, again for Dermot, this one. He was wondering, how do they perform NDT on the likes of the GE LEAP engine?
Typically in the aerospace and medical critical components, all components are X-rayed. So they would have an X-ray of any porosity or defect that would occur in those critical components. Yeah. And that's all digital now as well, so that would be kept on file into the future. If ever anything has to be referred back to, that can be pulled up and referred to. Yeah.
There's another one here linking into the porosity. John Coleman again asks, how is the porosity avoided, especially in complex shapes, and what effect is the effect of the powder geometry itself in ensuring a dense porous-free laydown?
So we do a lot of analysis of the powder because it is a critical. The powder has to be correct, otherwise the process itself won't work. If the powder should be spherical and it should have a good size distribution, for example, 10 to 60 micrometers or 10 to 40 micrometers, depending on the overall. It could be larger even. It tends to be a little bit larger for the direct energy deposition process. The powder quality from the supplier is important. The powder shouldn't have pores in it already, because those pores can then end up in the part afterwards. So you want to get a powder from the supplier that is spherical, good size distribution, and doesn't have already got pores in it. So you probably would tend to try and avoid water atomized powder, which might be a little bit less spherical and have a bit more oxide entrained. It is cheaper, so if you could use it, it could be a good thing. Another thing that you would see in additive manufacturing is that there's measurement of the humidity of the powder. If the humidity of the powder is too high, then this will lead to poor flowability of the powder, and the flowability of the powder is important, because it has to flow well to give the next layer for the part. Yeah.
Okay, great. The next one comes in from Joe. Thanks everyone for their interesting presentations, and asks you to explain how you would correlate the applied powder layer thickness to the resultant additive manufacturing part density.
Sorry, could you read that just one more time, John?
How do you, I think it's, I think he's asking, is there a correlation of the powder layer thickness and the part density? After the
so it's just at a very high level. If the layer thickness is too large, the top layer of that powder will have a higher temperature than the bottom layer of that powder. So your thermal gradient will be high, and that could lead to porosity. If the powder layer is too low, that could lead to an overheated layer, and overmelting leads to keyhole porosity. So too small is bad, too high is bad. So this is part of the design of experiments that is iterated to get to the right level. Yeah.
That's actually something I was wondering while you were going through your presentation. You were saying about the redistribution of the layer on top of the solidified layer, the layer of powder. How is that calibrated and achieved? Because it must have to be very
in terms of the laser powder bed system, you can very accurately control the vertical movement. So where the laser has been firing to create that two-dimensional solidified layer, that goes down by a very controlled prescribed amount, and the supply powder is raised, and the recoater blade then wipes that powder across like a squidgy. But because the control of the height is so accurate, you can get a very accurate amount of powder from one layer to the next.
Yeah, that's interesting. Thanks. Got a couple more in. This from Michael McMullen. Are there defined levels of porosity defects assigned to certain material classes, and are they dependent on the final function of the part?
I can answer that, but maybe Brian, do you want to take that? Yep.
We'll do it, Dermot. Yeah, I suppose in our case, it's actually defined to the functionality of the part. So the OEM, original engine manufacturer, will dictate the requirements in that. What we do is typically we did destructive sampling. So in our development process, we would carry out DOEs. We would look at porosity, like fusion, cracking, and so on, identify what the inputs are that affect that, and then monitor and control those. What we do then is we have representative test samples. in production that we would then destructively evaluate to ensure that our porosity isn't drifting in any way.
Okay, great. I actually had one for you as well, Brian. I was wondering, when you were going through the journey to find the application or the right method for repairing the parts, were there any other considered processes or any that came close, and what were the defining advantages of the process you chose?
Yeah, it was actually identified quite a number of years ago in conjunction with TWI initially. So LMD is actually used in a couple of different aerospace companies because it is suitable to repair. So our sister company uses it for different products as well in Germany. I'm aware of some more as well. New make aerospace would typically use powder bed because it's more design print. When you're adding to an existing structure, LMD tends to lend well to that because it's adaptive, and also you can deposit in full form, in full 5-axis as well. So we're not limited to vertical increments of Z heights. We actually can work at different angles and tilts as well. So you can get around the full structure of an existing body.
Okay. I think I've got one here for Fergal. Is there activity in standards development specific to LCF performance of LPBF aerospace alloys?
Oh, geez, you have me there. I honestly couldn't say without checking the list. I'll come back to you on it. I'll have a look.
No, that's fine, no problem. I've got one that asks, how can we enable the use of the materials effectively in medical fields? I suppose maybe is that asking how applicable to medical fields are these processes, maybe?
So maybe just to say that there's a lot of medical companies internationally using additive manufacturing to make implants, medical device implants or orthopedic implants for that are being used and have been used now for a number of years in surgery. Yeah. That does include the alloys, titanium and stainless steel. Other alloys would be applicable, could include nickel, titanium and cobalt chrome.
Okay, thanks for that. We've got one more question in here from Paul Borhan, just regarding the laser metal deposition and its percentage of defects that occur. That's a question. Is it quite a simple process for success, or is it a problematic process to carry out?
Brian, do you want to take that?
Yeah. Yep, I can do. I would say it's quite problematic. It's quite, you need to have a very balanced process, very stable. One of the really challenging factors with LMD is the blown powder side of it. So that creates its own difficulties in you have to control the powder focus, the powder density, the nozzle wear. You're talking about powder particles of microns traveling a distance of millimeters into a melt pool and trying to control that down to very fine tolerances. So there's quite extensive process parameter testing, DOE studies that take quite a period of time and a pretty long journey to get to that point.
Okay. I've got a couple of questions in the chat. Michael Sullivan asks, is there any application for M42 or D2 tool steels?
Just a general answer would be if it's metal as a manufacturable and there's an end application, then for sure, yeah, there could be, yeah.
There's one asking, what about the surface roughness of the finished components? is there any post-processing required? Or
so just to comment on the previous one, most metals are metal additive manufacturable. Just to confirm that, it shouldn't be a problem. Even merging steels that can't be cast, you can metal additive manufacturing them. So even alloys that are typically difficult, you can still come up with a process set of conditions that you can use for metal additive manufacturing. That question there,
surface roughness.
Surface roughness is usually higher within metal additive manufacturing, so it wouldn't be unusual that you need to go through a surface finishing technique, a post-processing technique in specific areas of the part after metal additive manufacturing. It could be grinding or electropolishing, for example. Yeah.
Okay. One for Fergal here from Robert Simpson. How do Standards Authority ensure that one particular company doesn't force their particular standard if they're, for example, a major player in the industry?
Really good question. Again, the participation on the standards committee is voluntary. So if you have just one company representing themselves on an Irish committee, that can very well happen. So it's up to NSAI then to market a new committee and invite stakeholders onto that committee. And all we can do is invite, because it is a voluntary activity, getting involved in standards. A lot of companies, when they see who is involved, they want to get involved themselves. And to be honest with you, it's not a negative thing, the standardization process. It's quite a good area for like-minded engineers to network with each other, even though they may be competitive in their companies. In the standards arena, they're like-minded and get on quite well.
A couple of questions about kind of the future direction. So one is asking, do any of the speakers foresee additive manufacturing being capable of creating large-scale structures, e.g. weight-optimized structural components for buildings?
Absolutely, yeah. There are some good examples internationally where in China and the US, they are printing buildings from concrete. And then in the Netherlands, they have the project where they're building bridges with robots in steel. So they're building the bridge in real time across the river or across the lake. The robots are just working their way across in a direct energy deposition technique, as opposed to laser powder bed fusion. So another interesting example is the development of 3D printing of clays for homes on Mars, is the project in the European Space Agency at the moment. So definitely, yeah, the 3D printing of buildings is a possible that we will see in the near future. Yeah.
There's one more here for Bryan. Michael McMullen asks, the Trent engine is a several decades old design. Do you have any difficulty in accessing the design data for some of the parts?
There's 2 points to that. One would be, it's a collaborative project with the OEM, so we're provided with all the required design data that we need for repair. So we work hand in hand on developing and optimizing that design to make it suitable for repair. So no, we don't have any access issues. Secondly, then we actually are working on the newer Trent engines at the moment, and we're actually moving into next generation extra wide body engines. So we're starting to move away from those older legacy ones.
That's all the questions that I can see in either the chat or, oh, sorry, one's just snuck in here, hang on. Do you think metal additive manufacturing is also applicable for oil and gas pipelines?
Yes, so where it could be applied in that case would be for the more high-end valve connections in oil and gas. Typical piping structures are just very easy and cheap for conventional manufacturing, so it would be for more high-end valve connections. There was one question around where other areas could additive manufacturing go into the future, and maybe just to say multi-material printing is an area that's going to increase, where you can print conductive and non-conductive and functional materials, for example, that will shapeshift as a temperature or a light source is applied to them. So those areas would be areas where additive manufacturing is going to expand more in the future. Yeah.
I think just to jump in there, actually, Dermot, as well, I know of in the oil and gas industry, there's a new DED process that they're utilising to coat oil and gas extensive lengths of pipework using ELA. So the guy LT Fraunhofer developed its extreme high-speed laser application, I believe. So it's very simple. It's an LMD process, but it's actually more like a coating effect. So what they do is they move the powder focus just above the pipework and they rotate it at extremely high speeds and coat it using an LMD type process.
Okay. It's quite similar to cladding process.
Exactly.
Yep.
Yeah.
Very interesting. Okay, well, I think all that's left to do is thank the panelists again. You can imagine the 40 odd people giving you a round of applause, and thank you very much for your time. And yeah, it was very informative, as someone has pointed out in the chat there. So thank you very much, and we'll see everybody for hopefully maybe we'll do another one in the future.